Okay, when we were last doing this, we were measuring the peak-to-peak voltage. And we did that by counting the number of divisions. In this case, we have 1, 2, 3, 4, and then about 0.4. If you use the little marks there, there's 5 little marks. Each one of those would be 0.2 of a division. So we have 2 more of those. So that gives us 4.4 divisions. And then we multiply that by the setting of the volts per division control here, and that's set at 0.5. So we would take to calculate that. Then we would multiply 4.4 divisions times the number of volts per division, which is 0.5 volts per division, and that gave us 2.2 volts. So our peak-to-peak voltage, VPP, is 2.2 volts. And then we wanted to go ahead and calculate the peak voltage peak, which is just abbreviated VP. Well, that would be half of that. VP is equal to VPP, or voltage peak to peak, divided by 2. So 2.2 divided by 2 gives us 1.1 volts. So that would be our peak voltage. Now we'd like to look at the timing of the waveform. Our circuit here is generating that waveform, and the timing is based on the value of this capacitor, which is called C1 in the circuit. Here's the schematic diagram of that circuit. Here's C1, capacitor 1, and then we have also two other resistors, two other components, resistors that are involved in timing, and that's R1 and R2, R1 and R2 here. And so one of those is right here, and the other one is on the breadboard up here. So now let's measure the timing of the period of this wave. In other words, how long does it take for it to complete one complete cycle? Now, one complete cycle would be like from the top of one cycle to the top of the next, or from the bottom of one cycle to the bottom of the next. So like from here to here, or from here to here, and so forth. Or you could use the you could move the waveform up and down on the screen. You could use where it crosses the zero, going down, like here it's going down, it crosses to where it goes down again here, so that like from here to here would be one complete cycle. Well, it seems to me that it doesn't matter which one we use, so we'll go ahead and the thing is, though, it's kind of the wave here is rather packed in on the screen, so I'm going to adjust the time per division control here to make the wave a little bigger on the screen so it'll be easier to measure. That looks good right there. I'll put it right there, and I'm going to count where it crosses zero, or I could do the peaks, it really doesn't matter. I'll count where it crosses zero going up, so like right here to right here. So that would be 1, 2, 3, 4, and one more little mark, so that would be 4.2 divisions. Or I could use the peaks. Let's try that. If I move it down, I'll use the peaks here and adjust it, the position of it with the position control knobs. Right about there. I could use the peaks, and that would be from here to there. Move it a little bit to the side. There, get it right there. So that would be 1, 2, 3, 4, and again about 0.2 or 0.3, something like that. Okay, I'm going to call it I guess I'd say 4.3. 4.3 divisions. Now, we would multiply that by the time per division, which is set right now at 0.2. 0.2 milliseconds. So the period will be equal to the number of divisions, which in this case is 4.3 divisions, multiplied by the time per division, which is 0.2 milliseconds per division. Okay, those two multiply together. So I can use my calculator here. 4.3 times 0.2 gives us 0.86 milliseconds. That's the time for one complete cycle. So in other words, the time represented from here to here, or one complete cycle, is 0.86 milliseconds. Now the other thing we could figure out from that would be the frequency. The formula for frequency is equal to 1 divided by the period. In this case, it would be 1 divided by 0.86 milliseconds. Now you got to be careful here. This is the period, and the period is measured in seconds. So if it's measured in seconds, we want to make sure that if we use milliseconds here, we don't make the mistake of simply taking 1 divided by 0.86. If we did that, well, we'd get very wrong answer. We'd get that, 1.16 hertz. Well, that's not correct, because we have to realize that this is milliseconds. So it's really, we could convert that to standard notation. We could write it as 0.0. We can move the decimal place 3 places to the left. Here we'd add 3 more zeros, so that'd be 0.0086 seconds. That's one way we could handle it. Or we could just let our calculator handle it. We could just go ahead and put it in as 0.86 milliseconds, which is 0.86 times 10, or exponent, to the minus 3. And then we're going to divide it into 1. So we press the 1 over x button. Now every calculator is different. This one, it's right here. There's what we got. We get 1,162.8, or that's what I'm going to round it off to. So our frequency then is equal to 1,162.8 hertz. Now we're really not measuring it that accurately, not at all. In fact, I'd just round that off to 1,160 hertz, and that's probably still being very generous as far as accuracy is going. Hertz is another name for cycles per second, by the way. I have another instrument here that's called a frequency counter, and this is an instrument which measures frequency. And I've got a test probe connected up to it here. So why don't I go ahead and connect that up to my circuit here and see what it says. I'm going to clip it on, see if it agrees with my calculation. Okay, it says 1,119 hertz. So it's a little different than what I calculated. The measurement, and that would be very accurate. This device is very accurate. So so you can see I have a little error there on the frequency. I measured it, and I was basing my measurement on the time period that I measured here. Well, I'm interpolating, based on the screen, And it's easy to make a little mistake one way or another, but that's pretty close. 1,119 versus 1,116. So measured is equal to 1,119 hertz. By the way, frequency is one of the most accurate things you can measure in electronics. If you want to measure something very precisely, if there's some way you can convert it to frequency, you can get a very accurate measurement. All right, so we've done it. We've figured out the peak-to-peak voltage. We figured out the peak voltage. We've figured out the period, and we figured out the frequency of this waveform generated by this circuit here. And we've also seen how we can use the oscilloscope. So go ahead and try those calculations on your own circuit using your oscilloscope if you have one available. If you don't have an oscilloscope available to you, you can use the values that we've just looked at here on our oscilloscope. And what happened to my waveform there? Oh, I see. Knocked a wire loose. So anyway, you can come up with, see what values you come up with your calculations. All right. Thank you for watching.